Throughout the long history of human civilization, the starry sky above has always been a wellspring of knowledge and imagination. Yet until recently, the full picture of our solar system remained an unsolved mystery. In the known planetary maps, Saturn long defined the outermost boundary. It was only with the invention of the telescope that William Herschel serendipitously discovered Uranus. But astronomers' calculations soon revealed inexplicable deviations in Uranus's orbit. This planet seemed to be pulled by some unseen gravitational force. This phenomenon hinted at another unknown world at the solar system's farthest reaches. Mathematicians then pursued this hidden giant through equations on paper. It wasn't until 1846 that humanity finally discovered a new planet through theoretical prediction rather than accidental observation. That planet was Neptune. When we gaze upon the vast, boundless cosmos, Neptune's immense distance dims the imagination. It silently orbits at a distance of approximately 4.5 billion kilometers from the Sun. This means that even signals traveling at the speed of light take over 4 hours to reach Earth from there. In this frigid realm, where sunlight is but a distant faint glow, Neptune reveals a vibrant, deep blue visage. This captivating blue does not stem from tranquil oceans, but is sculpted by the trace yet abundant methane gas in its atmosphere. Methane selectively absorbs the red wavelengths of sunlight, refracting a deep and mysterious blue light. Throughout the long history of humanity, our understanding of Neptune was limited to a faint, indistinct speck of light. We could not discern its surface details, sense its violent weather, nor comprehend its complex family of moons. This gap in understanding persisted for over 150 years. The turning point came in the latter half of the last century, at the dawn of the human spaceflight era. NASA launched its ambitious interplanetary exploration program, the Voyager mission. Bearing an epic mission, Voyager 2 undertook close-range reconnaissance of the outer 4 planets. After 12 years of interstellar travel, Voyager 2 finally reached its ultimate destination, Neptune, in 1989. This marked humanity's first true encounter with the blue ice giant. Not only did Voyager 2 confirm the existence of Neptune's ring system, it also discovered 6 previously unknown moons. It provided the first clear images of weather systems on Neptune's surface, including the famous Great Dark Spot, a massive storm system comparable in size to Earth. It even made a daring flyby of Triton, Neptune's largest moon, revealing active ice volcanoes on its surface. These unprecedented discoveries fundamentally reshaped our understanding of this distant planet. In the coming days, we will follow in the footsteps of these pioneering probes to delve deeper into the blue world at the edge of our solar system. We will dissect its internal structure, decipher its climate patterns, and marvel at the wonders of its rings and moons. Simultaneously, we will examine the latest observational images provided by the Hubble Space Telescope and the James Webb Space Telescope. These images continue to deepen our understanding of this dynamic planet. Now join me on this journey to the solar system's frontier, to visit the captivating blue planet, Neptune. The discovery of Neptune stands as a legendary chapter in astronomical history. It marked humanity's first successful prediction of an unknown planet using mathematical laws and physical principles. Previous planetary discoveries relied solely on direct observation with the naked eye or telescopes. Neptune's discovery was entirely different. It emerged from equations on paper. The prelude began with persistent observations of Uranus's orbital path. As early as the late 17th century, astronomers began meticulously charting Uranus's position in the night sky. Yet scientists gradually noticed significant discrepancies between Uranus's observed location and its orbit calculated using Newton's law of universal gravitation. The planet's trajectory seemed subtly guided by some unseen force. This anomalous perturbation sparked widespread attention and profound contemplation within the scientific community. The prevailing hypothesis posited the existence of a massive planet beyond Uranus's orbit. It was the gravitational disturbance from this unknown planet that caused the anomalies in Uranus's orbit. This concept inspired 2 young astronomers from different nations to independently undertake this arduous computational task. They were Urbain Le Verrier of France and John Couch Adams of England. Both scientists attempted to reverse engineer the possible location of this hidden planet through complex mathematical derivations. Adams completed his calculations first in 1845 and submitted his predictions to George Airy, the Royal Astronomer of Britain. However, perhaps due to the relative obscurity of the young scholar, his findings did not immediately receive the attention and follow-up they deserved. Meanwhile, working independently and unaware of Adams' discovery, Leverrier arrived at strikingly similar conclusions. Leverrier's prediction was forwarded to the Berlin Observatory, where the experienced observer Johann Georg Galle awaited its results. On the historic night of September 23, 1846, Galle received Levier's letter. He immediately trained his telescope on the celestial region predicted by Leverrier. To his astonishment, Galle discovered an unfamiliar blue speck, its position astonishingly close to the predicted point. After consecutive nights of observation, he confirmed the celestial body was moving relative to the background stars. This was undoubtedly the long-sought eighth planet. The discovery immediately sent shockwaves through Europe's scientific community. It marked not only the birth of a new planet, but also a brilliant validation of Newton's laws of motion. The power of science was thus revealed to the world with unprecedented clarity, proving humanity's ability to glimpse cosmic mysteries through intellect. An international dispute over priority of discovery soon erupted. British scientists insisted Adams deserved equal credit, while France vigorously defended Leverrier's contribution. To this day, the international astronomical community unanimously recognizes both Leverrier and Adams as discoverers of Neptune. The new planet urgently needed a name. Following the tradition of naming celestial bodies after Roman deities, Leverrier initially proposed naming it after his own surname. However, this suggestion was not adopted. Ultimately, the planet was named Neptune after the Roman god of the sea. This name perfectly matched the deep, ocean-like blue appearance of the celestial body as seen through the telescope. The discovery of Neptune dramatically expanded humanity's understanding of the solar system's boundaries. This was not only a triumph of astronomical observation, but also a great victory for human rational thought. This legendary tale of pursuing the stars with pen and paper will forever be etched in the annals of scientific exploration, inspiring future generations to continue venturing into the unknown. To grasp Neptune's nature, it must first be placed within the planetary classification framework. Neptune and its neighbor Uranus both belong to the ice giant category. This classification sharply distinguishes them from gas giants like Jupiter and Saturn, which are primarily composed of hydrogen and helium gases. The defining characteristic of ice giants lies in their cores, which contain vast quantities of icy substances composed of water, methane, and ammonia. Despite extreme heat and pressure deep within its interior, Neptune's equatorial diameter measures approximately 49,244 kilometers. This makes it the fourth largest planet in the solar system, following Jupiter, Saturn, and Uranus. Yet compared to Uranus, the third largest by volume, Neptune possesses significantly greater mass. This counterintuitive phenomenon profoundly reveals the uniqueness of Neptune's internal structure and composition. Specifically, Neptune's mass is approximately 17 times that of Earth, yet its diameter is only about 4 times that of Earth. This implies Neptune's average material density far exceeds that of typical gas giants. Its interior contains a higher proportion of heavy elements. To gain deeper insights into Neptune, we must construct layered internal structure models. The prevailing scientific consensus posits that Neptune possesses a solid core composed of iron-nickel alloy and silicate rock. This core's mass is roughly equivalent to Earth's. Its radius may account for 1/5 of the planet's total radius. Temperatures within the core may exceed 5,000 degrees Celsius, with pressures several times greater than those in Earth's core. Enveloping the inner core is Neptune's largest structural component, its icy mantle. This mantle layer is not composed of ordinary ice crystals as commonly seen. It is actually a supercritical fluid ocean formed by a mixture of substances including water, methane, and ammonia. This unique state arises when both temperature and pressure simultaneously exceed a substance's critical point. In this state, the material possesses the density of a liquid and the fluidity of a gas, blurring the boundaries between the two. Within Neptune's icy mantle, these so-called icy substances exist precisely as this fiery, dense, supercritical fluid. The icy mantle may extend tens of thousands of kilometers thick, accounting for the majority of the planet's total mass. Under extreme conditions, substances within the icy mantle may become ionized, acting as effective charge carriers. This property is crucial for explaining the origin of Neptune's powerful magnetic field. The outermost layer is Neptune's thick and dynamically varied atmosphere. Its primary composition mirrors the Sun's overall structure, dominated by hydrogen and helium. Hydrogen constitutes approximately 80% of the volume mixture, while helium accounts for about 19%. However, it is the trace components, particularly methane, that fundamentally determine Neptune's appearance and climatic characteristics. Methane gas strongly absorbs the red wavelengths of sunlight. This causes more of the blue light in sunlight to be reflected back into space by Neptune, thereby imparting the planet its iconic deep blue appearance. Beyond methane, scientists have detected trace hydrocarbons like ethane and acetylene in the atmosphere. These substances may be produced by photochemical reactions driven by solar ultraviolet radiation. Neptune's atmosphere is not uniformly static but exhibits a complex, layered structure. Based on theoretical models and observational data, its atmosphere can be broadly divided from top to bottom into the troposphere, stratosphere, and other layers. Within the troposphere, temperature and pressure increase continuously with decreasing altitude. This temperature gradient drives intense atmospheric convection, forming cloud bands and storm systems visible in the visible spectrum. Nautilus possesses an exceptionally powerful magnetic field with a highly unique geometric structure. Its polar magnetic field strength is approximately twice that of Earth's. However, Neptune's magnetic field exhibits two significant characteristics. First, the magnetic field originates not from the planet's physical core. The actual magnetic source lies more than half a planetary radius off-center. Scientists believe this phenomenon is directly linked to Neptune's supercritical fluid ice layer. It is precisely the flow of electrically charged matter within this icy layer that generates the planet's magnetic field. Second, Neptune's magnetic axis is tilted at a significant angle of 47 degrees relative to its rotational axis. This means Neptune's magnetic poles are severely misaligned with its geographic poles. This pronounced offset causes Neptune's magnetic field to trace an extremely complex trajectory through space as the planet rotates. When we synthesize these fundamental physical characteristics of Neptune, a clear picture emerges. It is not a simple hydrogen balloon, but a complex world, possessing a solid rock ice core, enveloped by a fiery, dense fluid ocean of ice, and crowned by a dynamic atmosphere. Its powerful internal heat source fuels the most violent storm system in the solar system, while its unique internal structure creates that peculiar tilted magnetic field. It is this combination of physical properties that defines Neptune's essence as an ice giant. Despite its distance from the Sun's heat, Neptune's atmosphere exhibits astonishing vitality and complexity. This distant ice giant hosts the most violent and active weather systems in the solar system. Its atmospheric activity far surpasses that of the larger Jupiter and Saturn. The primary energy source driving Neptune's intense atmospheric motion is not solar radiation. In fact, Neptune receives only 1/9 the intensity of sunlight that Earth does. Its immense internal heat source is the crucial engine sustaining atmospheric circulation. Neptune continuously radiates more energy into space than it receives from the Sun. This heat originates from residual gravitational potential energy accumulated during planetary formation and energy generated by radioactive decay within its core. This internal heat flux provides a sustained, powerful driving force for atmospheric convection. The most striking manifestation of Neptune's atmospheric ferocity is the extreme wind speeds recorded at its surface. With sustained winds reaching 2,100 kilometers per hour, Neptune holds the title for the solar system's fastest winds. This speed far exceeds any hurricane on Earth and approaches 1/4 of Neptune's own sound speed. High-speed air currents carry frozen methane cloud particles, forming intricate cloud bands and storm systems across the planet's surface. Images captured during the 1989 flyby of Voyager 2 clearly reveal a massive dark spot. Dubbed the Great Dark Spot, this storm system rivals Earth in scale and stands as Neptune's most iconic feature. Like Jupiter's Great Red Spot, the Great Dark Spot is an anticyclonic storm, yet its internal turbulence is far more violent. Unlike Jupiter's Jupiter's centuries-old Great Red Spot, Neptune's Great Dark Spot appears fleeting and ever-changing. When the Hubble Space Telescope revisited Neptune years later, the Great Dark Spot had vanished without a trace. The rapid formation and dissipation of this colossal storm vividly demonstrate the instability and dynamic nature of Neptune's atmosphere. Beyond the giant storm, Neptune's atmosphere hosts a rich variety of cloud formations. Most striking are the bright white clouds suspended in the upper atmosphere, layers composed of methane ice crystals. Driven by Neptune's intense vertical air currents, these methane clouds can rise far above surrounding cloud systems. In images captured by Voyager 2, these towering clouds cast distinct shadows onto their surfaces. This provides scientists with valuable data for measuring cloud heights and vertical atmospheric structures. In the deeper troposphere, scientists speculate the presence of cloud formations composed of compounds like hydrogen sulfide and ammonia. These lower-level clouds are typically difficult to observe directly, as they are obscured by the upper atmosphere. Another unique atmospheric phenomenon on Neptune is the persistent warming observed in the polar regions of its southern hemisphere. Despite enduring decades of polar night, temperatures in this polar zone remain higher than those in mid-latitude regions. This polar warming phenomenon is believed to be linked to Neptune's extreme axial tilt and seasonal atmospheric circulation patterns. The seasonal changes on Neptune, driven by solar radiation, follow an ultra-long cycle. With Neptune's orbital period around the Sun spanning 165 Earth years, each season lasts over 4 decades. This slow seasonal cycle provides ample time for the atmospheric system to undergo extensive adjustments and reorganization. Through continuous observations by the Hubble Space Telescope and the James Webb Space Telescope in recent years, astronomers have discovered a clear correlation between Neptune's global cloud coverage and its orbital position. When Neptune's southern hemisphere enters summer, both its global cloud coverage and brightness exhibit an upward trend. This further demonstrates that solar radiation remains a key driver of Neptune's climate change, even under extremely faint sunlight conditions. Nettle, the lead author of the study, noted that Neptune's atmospheric chemistry remains an active research frontier. Solar ultraviolet radiation breaks down methane molecules in the upper atmosphere. These decomposed carbon atoms recombine with hydrogen atoms to form more complex hydrocarbons like ethane and acetylene. These heavier molecules slowly sink into the warmer lower atmosphere, potentially aggregating into complex organic compounds. Ultimately, these hydrocarbons and organic compounds may condense into microscopic particles, forming the haze observed in Neptune's upper atmosphere. The essence of Neptune's dynamic atmosphere is a complex system primarily driven by internal heat, with solar radiation playing a secondary role. Internal heat flows generate intense convection and vertical circulation. Simultaneously, faint solar radiation shapes the thermal structure and seasonal cycles of the upper atmosphere. The synergy of these two energy sources ultimately creates the most violent and unpredictable climate in the solar system. Studying Neptune's atmosphere holds significance not only for the planet itself, but also provides crucial insights into understanding the numerous icy exoplanets prevalent beyond our solar system. Neptune does not sail alone at the solar system's edge. It possesses a complex and fascinating satellite system. This system comprises a series of planetary rings and a diverse family of moons. Together they form a miniature galaxy, maintaining a delicate equilibrium through gravitational interactions. Neptune's ring system ranks among the least understood in the solar system. In stark contrast to Saturn's bright, spectacular icy rings, Neptune's rings appear exceptionally faint and structurally fragmented. Composed primarily of minute dust particles and dark matter, these rings reflect sunlight with extremely low efficiency. Consequently, when observed from Earth, they nearly blend into the dark background, rendering them nearly undetectable. The 1989 flyby mission of Voyager 2 first confirmed the existence of these rings and captured backlit images that clearly revealed their complete structure. The Neptune ring system consists of 5 major distinct ring bands. The outermost band is named after one of Neptune's predicted discoverers, known as the Adams ring. The Adams ring is the most striking and enigmatic feature within Neptune's ring system. Several exceptionally bright, dense clumps known as ring arcs are distributed across this band. These arc segments resemble pearls on a broken necklace, forming discontinuous bright regions within the ring band. The most famous arcs are named Liberty Arc, Equality Arc, and Fraternity Arc. Upon initial discovery, these arcs appeared to defy fundamental principles of celestial mechanics. According to dynamical theory, these dense clumps of material should have dispersed within years due to orbital differences, eventually distributing uniformly throughout the ring band. Yet these arcs miraculously maintain a stable, clustered state. Scientists now believe this stability stems from gravitational resonance between the arc band and neighboring moons. The small satellite Galatea, orbiting beyond the Adams ring, exerts a shepherding gravitational influence that restrains particles within the arc bands, preventing their dispersion. Beyond the Adams ring, Neptune possesses multiple ring systems, including the Verrier ring, Galle ring, Russell ring, and Arago ring. These ring bands are generally narrow and exhibit uneven material distribution. The Verrier ring is another relatively intact band, though its material density remains exceptionally sparse. Scientists speculate that the dark matter within Neptune's rings may be rich in organic compounds. These substances gradually darken due to prolonged exposure to cosmic radiation. The material within the ring systems is unlikely to be primordial remnants from Neptune's formation. A more likely scenario is that these rings consist of debris from comets or small celestial bodies colliding with Neptune's inner moons. The dust fragments produced by these impacts gradually dispersed and were eventually confined to stable resonant orbits, forming the ring system we observe today. Thus, Neptune's ring system may be a relatively young and dynamically evolving structure. Compared to the rings, Neptune's satellite family exhibits even more astonishing diversity. The 14 confirmed moons to date vary greatly in size, shape, and orbital characteristics. The largest moon is Triton, discovered almost simultaneously with Neptune itself. With a diameter of approximately 2,700 kilometers, it ranks as the seventh largest satellite in the solar system. It dominates Neptune's satellite system, accounting for over 99.5% of the total mass of all other moons combined. Its most distinctive feature is its unique retrograde orbit, rotating in the opposite direction to Neptune's rotation, a phenomenon unparalleled among major moons in the solar system. This anomalous orbit strongly suggests Triton did not form synchronously with Neptune within the protoplanetary disk. It most likely originated from the Kuiper belt, captured by Neptune's gravity as an independent object. Intense tidal forces during capture heated its interior, potentially triggering intense early geological activity. Triton's surface is covered by a layer of frozen nitrogen and methane, presenting an unusually flat terrain with very few craters. This indicates an extremely young geological age, with the surface undergoing continuous renewal processes. The Voyager 2 spacecraft captured images of multiple active geyser eruptions on Triton's surface. These geysers propel dark organic compounds or nitrogen ice particles several kilometers into the atmosphere. Such eruptions may be triggered by faint sunlight penetrating the semi-transparent nitrogen ice layer, heating the volatile substances beneath within the solar system. Only Triton and a handful of other moons, such as Ganymede, Jupiter's moon, and Enceladus, Saturn's moon, exhibit such active geological processes. Beyond Triton and Neptune's satellite Nereid, another unique Pluto moon stands out. Nereid possesses one of the most eccentric orbits among all known moons in the solar system. Its perihelion approaches Neptune at just 1.3 million kilometers, while its aphelion extends to 9.6 million kilometers. This extreme elliptical orbit likely stems from complex gravitational interactions with Triton. During Triton's capture by Neptune and subsequent tidal rounding, its orbital path underwent significant perturbations. Other inner Neptunian moons like Proteus, Saturn VIII, and Larissa, Saturn 7, similarly exhibit irregular shapes and heavily cratered surfaces. These bodies likely originated within the Neptunian system, forming within the protoplanetary disk surrounding the planet. The gravitational influence of these small satellites is crucial for shaping and maintaining the complex structure of Neptune's rings. Acting as shepherd moons, they clear gaps between ring bands through gravitational resonance and constrain the diffusion of ring particles. For instance, Proteus's orbit precisely occupies the gap between the 10th and 11th rings, where its gravity effectively prevents ring material from invading this region. Nettle's ring system and satellite family together form a dynamic laboratory, where we witness firsthand how gravity shapes celestial orbits, how tidal forces drive geological activity, and how collisions and captures alter planetary evolution trajectories. This miniature galaxy is not only Neptune's treasure, but also a key to understanding the solar system and exoplanets. Our journey exploring Neptune is drawing to a close. Together, we trace the epic journey of discovery from Galileo's hazy observations to Voyager 2's historic flyby. We explored the icy giant's peculiar internal structure and its dynamic, violent weather systems. We marveled at its slender yet intricate planetary ring system and its astonishing family of moons. As the sentinel of the solar system's frontier, Neptune has fundamentally reshaped our traditional understanding of distant worlds. This seemingly silent, frozen realm actually harbors surging energy and active geological processes. The data and images transmitted by Voyager 2 in 1989 merely opened a fleeting observational window. Yet this glimpse was ephemeral, leaving far more unanswered questions than revealed truths. What fuels the persistent ice volcanoes erupting on Triton? How does Neptune's internal heat flow generate the solar system's most violent storms? Can the mysterious arc-shaped structures within Neptune's rings maintain their current stable form forever? These questions continue to challenge the wisdom of astronomers worldwide. Behind each puzzle lies a cosmic mystery about planetary formation and evolution. This is precisely why Neptune is so captivating. It represents the frontier of human understanding. Now, I'd like to pass the microphone to you, our fellow interstellar travelers watching at home. Among today's shared insights and imagery of Neptune, which scene left you most awestruck? Was it the stark contrast between its serene, deep blue surface and the violent storms raging within? Or the daring solo interstellar voyage of Voyager 2? Perhaps the eerie spectacle of nitrogen ice volcanoes erupting on Triton? Share your most profound impressions and reflections in the comment section. Every insight you offer may spark brilliant intellectual exchanges. If you were designing future Neptune science missions, what would be your primary scientific objectives? Would it be deploying balloons to probe its atmosphere? Or landing a rover on Triton? Or perhaps an orbiter dedicated to studying its magnetic field and ring system? Let your imagination run wild and share your visionary concepts with us. Your unique ideas could point the way for future space exploration. If you wish to continue receiving in-depth content revealing the mysteries of the universe, be sure to subscribe to our channel and click the little bell icon. Your subscriptions and support are the greatest motivation for us to keep creating quality science content. In our next episode, we turn our gaze to another captivating celestial body. Let's explore together the ocean worlds within our solar system that may harbor life. Europa, Jupiter's moon, will be the star of our next video. Beneath its icy crust may lie the solar system's most promising frontier for life. This new adventure about to begin is not to be missed. We look forward to reuniting with you on our next exploration journey. Thank you for your attention and companionship today. May you always keep your curiosity about the universe alive. See you in the next video.